Welcome to our Power 100 webinars. I'm Alberto Ravagni from InfraPrime. In this webinar, Susanna Cass, Jack Brower, and myself will provide a deep dive into carbon-free energy from theory to practice. Susanna Cass is co-founder of InfraPrime, member of Climate 50, data center advisor to the United Nations Sustainable Development Goal Program, energy fellow at Stanford University, and recently she had the privilege to be elected in the Power 100 Global Index of the most influential people in the wholesale carrier community. Professor Jack Brower is Professor of Mechanical and Aerospace Engineering at the University of California, Irvine, and Director of the National Fuel Cell Research Center.
Thank you for spending the next 30 minutes with us. The fundamental pillars of data center is to be resilient, be accessible anytime, anywhere, and be available of all the resources, including the energy capacity, and be elastic to support the human and machine users. As the data center advisor for the United Nations Sustainable Development Program, working with hyperscaler every day and leading cloud providers around the world, I found it is insufficient. We need to design and rebuild into a more sustainable future. I share the passion with many, and today with two of my esteemed colleagues in this net zero journey. The topic is really a simple concept of net zero. It just makes good business sense. Data center clearly has become a beneficiary due to COVID-19. It altered the landscape of the digital infrastructure for most of us that most likely will be able to work from anywhere, maybe for the remaining of the year in 2020. Well, we hope so. The infrastructure that supports us 24/7 should be built with net zero, zero carbon, zero emission, and zero waste. And in our consumption of environmental resources, we also need to be socially responsible. The ESG fund manager, interestingly enough, continued during the pandemic, outperformed the broader market, meaning the topic that we're going to discuss with you for any net zero assets are becoming more valuable in terms of the asset class. So this is crucial because the data center industry is spending $1 billion a day, even during the pandemic times, in terms of the slowdown of the construction in building data center. So I am extremely excited to introduce you to our first speaker, Professor Jack Brower, who leads the National Fuel Cell Research Center. He received his education from MIT and currently is a professor at UC Irvine for mechanical and aerospace engineering, civil and environmental engineering. I know he is extremely passionate about his research and his findings are astounding. And thank you so much for spending the time with us today, Professor. And I will turn that over to you now to talk about clean energy transition, how we can alleviate the use of fossil fuel, costly electricity, and the transition of net zero for the data center industry. Thank you, Professor.
Thank you very much, Susanna. I'm happy to be here today and to talk about net zero, not only for data centers, but for the world. It is inevitable that primary energy will come to us from the sun and wind power that is geographically available all around the world. It's available in different measures, depending upon where you are, but solar and wind power will be the primary energy that we use forever in these jurisdictions. And if you are to gain all of your energy input from these renewable sources, there is a challenge, and the challenge is reflected by this simulation that we accomplished in California. In this particular case, we simulated the actual wind and solar dynamics for making California 100% renewable. We needed to install 37 gigawatts of solar capacity and 80 gigawatts of wind capacity. And what you can see is that there are deficits during certain periods and surpluses at other periods, but the total amount of surplus is greater than the total amount of deficit. so that the energy amount produced by this solar and wind capacity is sufficient for California to become 100% renewable. Now, this is an example case for anywhere in the world and even for a data center, for example. So what do we need to do? All we need to do is to store the surpluses when they are available and return them to the deficit periods when they are available. And today we do that using pumped hydro primarily. And California has a very large pumped hydro system. This is how large it is in comparison to this annual simulation. If you could turn all the pumps on at once, it's about 9 gigawatts of electricity that it could consume. That determines the height of this box here. And the area of this box is the energy amount that could be returned to the California grid if all of the upper lakes were drained and through the turbines produced electricity by hydropower. So if you look at this pumped hydro system that we have in California, it's pretty apparent immediately that it is insufficient to capture all of the surplus. Some suggest that we could add batteries to this, or to use vehicles, battery electric vehicles, to store some of this power and return it to the grid at other periods. If you were to convert all the light and medium duty vehicles in the entire state of California to battery electric vehicles and use them only for absorbing the surplus and returning the deficits, this is how large that resource would be. It has a lot of power capability, as you can see by the height of this, but the amount of energy that these 21 million EVs contain is quite small in comparison to the need for making it through the year. There really is only one existing resource that is sufficient to move all this energy around and make the state of California 100% renewable, and that is to use fuel storage. We already do this with the natural gas system. But if we used existing gas storage resources and put renewable hydrogen into those resources, this is how large that resource would be. In other words, we don't need to build any new storage facilities. We just need to get rid of the fossil that's in them and put renewable hydrogen in them instead. And we would have an energy storage resource that has power that is sufficient to capture all of the surpluses and a massive energy amount that even could enable the total capture of this excess in the summer months and delivering it to the deficit months in the fall and winter. The only current storage resource that is sufficient is renewable hydrogen. Batteries end up just not being big enough to enable 100% conversion to solar and wind power in California. And how do we make this renewable hydrogen? Well, we make it via electrolysis. Electrolysis takes water plus the renewable electricity and makes hydrogen and oxygen. And typical efficiencies are between 60 and 90%. And every liter of water yields about a normal cubic meter of hydrogen. And there are various types of these electrolyzers, which with renewable electricity and water can produce the hydrogen and oxygen that we need. Alkaline electrolyzers are currently the lowest cost and have the highest efficiency, and they're widely available commercially. Proton exchange membrane electrolyzers can operate under pressurized conditions and can be highly dynamic in their operation. They are also widely available commercially. And solid oxide electrolysis systems are emerging, not as widely commercially available, but they have the potential to go to even higher efficiencies than alkaline or PEM. The fact of the matter is that we already have commercial, and reasonably priced electrolysis technologies for making this green electrolytic hydrogen for this purpose. Now, I want to drive the point home with regard to the energy storage need by not only considering the California case, but considering the world, because the whole world needs to be converted to zero emissions. And if we did that using only solar and wind resources and understood the dynamics of those resources in all the continents, then to make it through 1 year, we would need almost 20,000 terawatt hours of energy storage. This is a massive amount of energy storage. And if you tried to make a single battery that would last only about 5 years, you would need about 3,000 megatons of lithium and about 25,800 megatons of cobalt for the state-of-the-art lithium-ion batteries. If you look at the US Geological Survey and you try to determine how many megatons of lithium and cobalt we have on Earth, you would find that we only have 53 megatons of lithium all around the world, and only about 25 megatons of cobalt on terrestrial resources. If we mined the ocean floor, we could get another 120 megatons, but you can see that it's quite obvious that if we wanted to store all of this renewable solar and wind power in lithium-ion batteries, the very best batteries around the world, there is insufficient lithium and cobalt. We couldn't do it because there just isn't enough lithium and cobalt around the world. Not to say that we also have child labor practices and unfriendly countries that we often have to deal with to obtain these resources, like the Democratic Republic of Congo. So there's not enough lithium and cobalt in the world to make batteries sufficient for enabling 100% renewable. And we should use these precious resources for the kinds of applications that need high energy density, like cars and cell phones. So I say focus that resource on what we need for zero emissions. When we need zero emissions in all end uses, it is imperative that we need a zero emissions fuel for some applications. And these are the applications that require rapid fueling, long range, or large payload. So shipping or aviation, some bus routes, trains, or long haul trucks. In these applications, renewable hydrogen can meet these demands, but electrification through battery electric options cannot meet these end uses. So now let me transition a little bit to data centers, because data centers can be made 100% renewable by using only solar and wind inputs. But then of course we need to, just like we did in the world and in the California case, store the renewable energy when it's available in excess and deliver it back to the data center when it is available in deficit. So these are just 3 configurations that we considered. One takes batteries, lithium-ion batteries, and stores the renewable electricity when it is available in excess, provides that renewable electricity to the servers when it is available, and then takes it from the batteries when it is available in deficit. We could also make hydrogen energy storage instead of battery energy storage the option we consider, where the electricity from the solar and wind power goes to the servers, and when it's available in excess, it goes to making hydrogen, and then we use fuel cells to power the servers when it's available in deficit. We also could have a simplified system that takes all of the wind power and makes only hydrogen, and then only uses fuel cells to power the data center. This is really a stark configuration that Microsoft has pioneered. So let's consider these 3 configurations, and let's look at 100% renewable data centers. I want to point out that electrolysis and fuel cell conversion of that renewable electricity is less efficient than the batteries are. Batteries have a higher round trip efficiency than we can achieve with electrolysis or fuel cell technology. But that's not the only metric that is important, because when we simulate the annual achievement of zero emissions, one must consider a lot of other things. So for example, this is a 20% wind, 80% solar case, okay? And we can allow for some curtailment. What does that mean? That means that we install more solar and wind power than we need to make it through the year, and we allow it during some periods of the year to be curtailed. And if we just let 5% of the power be curtailed, we can have a greater than 20% reduction in the electrolyzer size for this particular power to gas case. And you can see the dynamics for a couple of weeks here in January, where you can see that this is primarily solar. That's why we have this daily peak that occurs. And the red is where we have wind power available, and we meet the data center power and store the excess. And if we allow curtailment in the 10 to 20% range, you can see here, then we have the lowest, smallest storage size that is associated with meeting the data center power with only sun and wind power. And here you can see the total state of charge for a whole year of simulation for various amounts of curtailment. So you can see, in some cases, we can make the storage system smaller, like this red case that makes it all the way through the years, whereas this green case has a larger energy storage system that is required for the dynamics of making this data center 100% renewable. And I want to give an example here of why we want to use both solar and wind. Here is an example for Wyoming, in which case, if we have 0% wind and 100% solar, the storage that is required to make it through the year is shown here. But if we just add 15% wind to that solar case, you can see that the magnitude of the storage that is required to make it through the year is dramatically reduced. And that's partially because we have semi-complementarity associated with the wind and the solar. So let us go back then to all three of these configurations that I introduced at first. And we can size these for the lowest cost, the lowest capital cost. And in each case, there's a different configuration. So for example, in the battery storage case, we want 20% wind penetration. That gives us the lowest capital cost. But the capital cost for this is actually quite a bit higher. It's actually double the capital cost of this power to gas case. And that's primarily because of the separate power and energy scaling that is possible when we go to renewable hydrogen. Even though we have to install much more renewable energy because the round trip efficiency is lower, the capital cost is halved because we can separately size the storage tank and the size of the electrolyzer and fuel cell. The cheapest case, as a matter of fact, is this case where we go to excess power to gas, meaning that when we have solar and wind power available, we deliver it to the servers. When it's available in excess, we make hydrogen, and when it's available in deficit, we take it out of the hydrogen storage and put it through fuel cells to power the data center. So with that, I want to return it to Susanna. Thank you.
Thank you, Professor. This is amazing because it genuinely delivered the net zero results in terms of utilizing one resources more efficiently than the other. So with that, I think I'm going to turn it over to our second speaker, Dr. Alberto Raffani, and talked about how we can actually bring net zero in a carbon-free energy architecture into practice. And then we'll open up more questions so we can welcome you back to share your thoughts again, Professor. Is that okay? So Alberto, why don't we take it over?
Thank you, Susanna. An excellent presentation. Wonderful. Let's see now how we can convert or build data center with carbon-free energy in practice. And we start with the status quo. So the power characteristics or the requirement for data center are very high resiliency. That's one of the priorities. 24/7 uptime, 99.999% availability. For those of you who are not familiar with this, that means 5 minutes outage per downtime per year, which is really little. They're usually powered by grid power, and they use backup generators. And they look like this, not really attractive. And especially those diesel backup generators are something we would like to substitute or get rid of as soon as possible. Okay, just to give you some numbers, why these 5 nines requirements are needed. Referring to California again, in October 2019, there was a pretty long power outage, 48 hours, and for 800,000 customers. And the cost of that outage was estimated at about $2.5 billion. Okay, so outage are, as we said, not only for data center, but for the whole economy, are extremely heavy. Now, because of this reason and others, again in California, still with all the pledges that the data center industry have made to clean and carbon-free power, there are still about 650 megawatt of diesel backup generators which have been submitted for approval to the Energy Commission. Replacing those diesel generators is not anymore an issue about technology availability, it's an issue about having a right mindset and choosing the right solutions. So how do we do it? How do we power data center with carbon-free energy? Of course, the requirements are the same. It has to be resilient 24/7, 5 nines availability. It has to have a dual power input in order to guarantee that kind of uptime. It has to be carbon-free or even carbon negative. We have heard the recent pledge of Microsoft to remove the carbon that has been generated. We don't want any diesel generators, and most importantly, it has to be also affordable. Now, one architecture, one design that fulfills the requirement is this one here on the left side. Here you have fuel cells which use hydrogen or renewable gases. Together with battery, they generate carbon-free energy on-prem, on-site. We define a power availability zone, which is familiar to data centers, with a power duality. The primary power is renewable gas, which, as we have said before, can be hydrogen. The grid is there as a backup. Okay, and this power duality is both available at the power availability zone and also at the single data center element level or at the pod level. And with this architecture, with this configuration, you can build a microgrid with multiple layers of reliability, and you can achieve the all the requirements, fulfill all the requirements above. A second example, and a second architecture, is the one on the right. Here, we replace the diesel generators with fuel cells and hydrogen and batteries. Here, the grid power is the primary power, okay? And the fuel cells and batteries are the backup solution. So again, on the left side, fuel cells are always on. They are the primary power. On the right side, the fuel cells are the backup. They're usually off and they come online when there is an outage. However, the batteries, they have a very important function. They can enable the data center to achieve what we call the 27 carbon-free matching, which is now the new standard. As you know, data center operators, they purchase impressive amounts of wind and solar power with renewable certificates. Now that is not sufficient anymore. That's an average value of the energy that you use through the year, but it's not sufficient to guarantee that in every hour of the day, in every moment, your data center is powered by renewable energy. There will be, if you use only certificates, there will be time of the day or of the year where you are powered by the fossil component of the grid power. So using the battery, you can, when you can purchase renewable power from the grid and shift it and store it so that you guarantee the 24/7. Okay, that's very important for them. How does it look like in practice? How does fuel cell, let's say, look like in operation? Well, you can have fuel cell at the rack level. And this one here is a project for which I'm very proud. I have to mention that Jack played also an important role in this project. He made all the testing of the fuel cell where will be delivered to this project. The project is a data center. It's actually the Advanced Energy Lab in Seattle. It's a Microsoft data center used to demonstrate that you can build a gas-powered data center which is not connected at all to the grid. This is symbolized by the electric cable which has been cut instead of the ribbon during the inauguration. Okay. The fuel cells for this kind of configuration are being tested. They are commercial solutions which still need to be proven and tested for a longer time. Yeah? But they look like this. They look like kind of servers, and they can be installed, as you see here, at the same level, really in close proximity to the servers. You can deploy fuel cell at the pod level. That's another solution which we are developing and we have designed within InfraPrime. In the middle here, you have an EcoPrime power module with 480 kilowatt. And these provide the power for 2 EcoPrime power modules, each with 200 kilowatt of IT load. And you see here too, the power duality, which is given by the renewable gas as primary input and the grid power as the backup solution. And again, no generators. And many of you will probably be familiar with the Bloom Energy servers, which are deployed on site. So that's fuel cell at the site level. But for the data center, there is no difference from the electrical distribution, like the power would come from a substation. Only that the power is generated on site, starting from natural gas or hydrogen in these fuel cells, and each of those rows are about 1 megawatt of power. Now, in practice, we want to achieve and to deliver a sustainable count of ownership, meaning that sustainability is not having to choose between the environment, the society, or the profit. We want to deliver the triple bottom line, and sustainable and affordable must be the same thing. How do we do that? Well, starting from the status quo, which is 100% of the cost, we simplify by eliminating the diesel generator cost. We don't have them. When you use renewable gas, you don't have the power bill. That's another very big cost saving. In many cases, we can simplify the electrical distribution capex to have a Stark architecture. That was one of the main goals of that proof of concept of Microsoft in Seattle. And of course, you have to add some of those costs because of the fuel cells and the batteries. And alone like this, with the right design and the right scale, the carbon-free energy is a lower cost. It is more convenient than the status quo. Okay. In addition, in many states, in many situations, there are incentives related to using and producing zero carbon. So the net zero solution with carbon-free design is affordable. The solutions that we propose are affordable and competitive compared to the, let's say, carbon or the dirty grid, as we call it. So to summarize, the zero energy data center characteristics are exactly like the one, the status quo, with resilient 24/7 uptime, 99.999 availability. It is affordable. They can be delivered for your site now. There are solutions available now. No reason to wait or to wait to replace or to design your data center without diesel generators. And there are many ways to offer them as a service, paying a monthly fee and avoiding the CapEx expense. And with this, I turn it back to Susanna.
Thank you, Alberto, and thank you, Jack, for sharing with us some theory to practice on how carbon-free energy is going to deliver net zero. And to Jack's point, this is not just limited to data center. I think we should just basically make good sense of it. in summary, I guess I'll turn over to you, Jack and Alberto, in that order. Can you do a quick takeaway for the audience today, what they should learn from you? Professor, let's go with you first.
Thank you very much, Susanna. The key thing that I think is that we must understand the magnitude of the problem and challenge that is ahead of us. And when you consider the magnitude of the challenge for going to 100% renewable throughout society and in all end-use applications, including data centers, then we need more than just the existing solutions that people are putting into practice. We need more than just sun and wind power and batteries. We must make a renewable fuel. And many jurisdictions around the world are discovering this and agreeing to invest in renewable hydrogen as part of the solution. We absolutely need the solar and wind and batteries, but we also need renewable hydrogen to achieve our policy goals of zero emissions.
Thank you, Professor. Dr. Alberto?
Yep, I'll do as fast as possible and confirm that yes, your next data center and even your current data center should design and think it as a carbon-free data center. The technologies are available today, and they are a combination of solutions. As Professor Bravo said, it's not only one technology that will lead you to this achievement, to this milestone, but combining different solutions, it's a goal where you can start working already today. So start immediately to get rid of the diesel generator and start your path to get to net zero and carbon-free energy.
Thank you for both of you, and thank you for the audience for joining us today. For those of you who might be interested in knowing how net zero can be put in practice in real location, we have prepared for you 2 webinars in July that you can see on the screen. On the 15th, I'm very excited that one of our colleagues in InfraPrime will be joining us, Ferris Ellis, who will be leading the discussion on net zero data center with amazing power usage effectiveness of 1.09 and showing a case study in the Nordics. And then in the 29th is definitely one of my passion. Alberto and I will come back on again to talk to our colleague about how we clean up the dirty cloud, specifically in Ashburn and Virginia, that we all know dearly, that it's not clean right now and definitely should be taking advice from Professor Jack Bauer on using renewable gas fuel, which makes a lot of sense, and then we'll put that in practice. So with that, I thank everyone for joining today. Thank you again to both of you, our esteemed speakers, and continuing your work in actually helping to build a more sustainable future for all of us. Thank you and have a very nice day. This will conclude our webinar now. Bye-bye.
Bye-bye. Thank you, Susanna.